Good evening, sir. Hello. Hello.
Okay, good evening, Pratham. Hello, Pratham, is it audible? Hello, Pratham.
Can you hear me, sir?
Yeah, good evening. Okay.
Good evening, sir.
So in the today's class, I'll end this chapter. Okay.
Okay.
One topic is there, but I feel that topic should be covered in your current electricity part. Okay, along with the resistance topic. So yeah, that your teacher will cover in the current electricity itself.
Okay, sir.
So I'm sharing my board. Okay, so just wanted to know the reason till where I can. Just a minute. I make something like this. If I want to export this. Okay. It is okay. So the Pratham, what we discussed in the earlier is dielectric, right? So last thing I will discuss that is polarization in a proper manner. After this, just application and we'll end the chapter. Okay.
Okay.
Look, in basic polarization, we already covered in the last class that if you have some body like this, if you have some body like this, and let's say this is positive, not positive actually, this is positive, negative, positive, negative, positive, negative. These kind of charges are there. Okay.
Okay.
Then, yeah, if these kind of charges are there,
Mm-hmm.
positive, negative, positive, negative. Okay. Now, you have two options. One is we can have the similar thing, but in two scenarios that if you don't have any charges, let's say electric field, external electric field is zero, then the charges will rest like this. Okay. Another option is you have some electric field which is not equal to zero. Okay.
Okay.
Now it depends upon the direction. If the direction is like this, then all these charges will align themselves like this. They will align themselves. Yeah. What they are going to do is, okay, here. So here they will be aligning something because electric field is this way. Okay. So what will happen? They will align themselves along with the dipole moment. What is dipole moment? It is if you have positive charge, if you have negative charge, right? So what they do, this is we call as a dipole moment, right? From negative to positive. So
Okay.
aligning with dipole moment, what's the benefit of it? Let's say these are the pair of charges, right? This negative becomes this and positive because I'm saying this dipole will align, so it will be aligned like this. Clear?
Okay.
All
Yes.
three. What's the benefit of this? Earlier, this is positive, this is negative, right? Now you had to align it with this because if you see, it is like this, right?
Yes.
If you see, and we have already discussed about the torque in dipole.
Yeah.
Or you can say energy in a dipole. What was that? Minus PE. Currently you can see it is 90 degree, right? Cos 90. What is it? Zero. You have zero energy. I know that thing. But what if you align yourself with the electric field? If you do so, this angle is zero. This comes out is zero. Whatever the value is, negative. You have lesser potential energy. Understood this point? What does this mean? Your negative potential energy is like you are more bounded to the thing. Okay. You're not in the excited state. You are in the very grounded state. So this is more stable state as compared to some positive or zero energy state. Is that clear?
Yes, sir. It's
And
clear.
okay. Another way you can think of it, you have two options to alignment. if with this electric field, one is positive negative and negative positive. If you see, this is electric field going outward, I can say somewhere here a positive charge is there. To seeing a positive charge, who will try to go closer to that? A negative charge, right? Not a positive. So this is not a possible thing, this is a possible thing. And we can say in these cases we have a dipole moment which align themselves along with the electric field, right? So
Mm-hmm.
this is what the polarization happened. Now we have multiple type of polarization happening. Polarization. Okay, it's, you can see these are kind of some dielectric which you have put into the electric field. You can see in the capacitor cases we have already discussed. Okay, so
Okay.
polarization is basically, we have three kind of polarization we can discuss. So first one is electronic polarization. Electronic polarization, what does this mean? It means that when you provide an electric field, right, electron when if this happens when your electric field displaces the electron cloud to some relative position. Okay, for example, if you have applied like this, if you have applied a elect, electric field, okay, in this case if I say you have some electron cloud like this, positive charge electron cloud, lot of positive, right, and you have some negative charge. By seeing this, what happens, all the negative will shifted to one side, all the positive will shifted to one side, right? You can see by using a electric field you have taken whole cloud of charge, right, and the relative position. Is that clear?
Yes.
This is your electric polarization. Next one is ionic. In ionic, what happened, uh, if you see all the electrons and protons, for example, if I have this material, wait, I'll just write ionic polarization. Okay, so this is, in this case what happened, let's say this is a metal you have, this is metal you have. Okay, in this what happened, you know, lot of electrons are there, lot of protons are there. Okay, they will align themselves along with the electric field. Okay,
Okay.
this is the first thing which we have discussed about the polarization. This is similar to that thing. And the last is oriented polarization. In this what happened, dielectric, the permanent dipole moment is created. Okay,
Okay.
so that's the thing. In this third one cases the permanent happens. This is all about the polarization. One
Can
formula
you,
is,
sir,
what happened,
summarize all of them once?
summarize all of them.
Yeah.
In this what happened, electrode electron cloud, electron cloud aligns themselves.
Uh-huh.
Okay,
Okay.
okay, in the, in the next one which is ionic one, in this what happen, if you have some ionic bonded, right, ionic bonds, if you have electric field, it causes the, it causes shift, it causes the shift of positive and negative ions, okay, in opposite directions. For example, if one atom is there, let's say this and this, you have this kind of bond. That's obvious thing, a bond is there, it must be due to some positive charge, negative charge. By seeing this electron, what will happen, like by this seeing this electric field, what will happen, it will cause the positive and negative ion to shift. Okay,
Okay.
this is positive, this is negative,
Mm-hmm.
electric field is this, what will happen here, again this will shift. Clear?
Leo.
So this is the shift of thing. And the third one is, let's say very random electron pairs are like present. Okay, in this happens generally in the dipole. First two can happen in metals also, these first two can happen in metals also. The third one is, let's say this is the example of third one also, this is the main example of third one also. Orientation. Orientation is basically dielectric, right? In the dielectric you have positive charges, negative charges are pairs, all of them.
Okay, sir.
What can you take an example of dipole? If you see water molecule, what is the water molecule? Hydrogen, oxygen, hydrogen,
Yes.
two lone pair, is it?
Yes.
Okay, so you can see hydrogen have a proper dipole at a one direction.
Yeah.
Okay, now what happens if you see, even if we say like this is, that's why this can act as an electric field. Understood? Because it has a proper dipole moment.
Okay.
Okay, even after it is a non, it provides a non-conducting nature, but it has a dipole moment. It is a polar molecule because it has dipoles. Okay, those materials, for example, if you put electric, if you put thing, wooden thing will never be able to provide charges at these interfaces. Understood? Because they don't have dipole moment to be created. It's not a polar molecule. Being a polar, like being a dielectric and being an insulator, is a different thing. Understood that point? A
Mm.
dielectric can have a polar nature which can be useful for polarizing the internal charges. The best example is water molecule, which is a polar. Okay,
Okay.
orientation. Because in like if in water, it's not necessary that if you don't have electric field, your water molecules are freely to be present in any, like any configuration, right? Someone will be like this, someone will be like this,
Yes, sir.
right? You provide an electric field, all will be like this, this, something like this. Okay, these are the dipoles which is aligning themselves. So that's the thing. This is all about the polarization. Yeah, one formula I was about to discuss, that is P. How much polarization is going to happen? It is basically the total dipole moment divided by volume. This capital is polarization. Okay, you can see till now dipole moment we used to write with small p. This is capital. So that's the difference. Clear?
Yes, sir.
Okay, so look, by this we have done the capacitance chapter. Okay, I'll just go with some. I will explain it. Okay, not I will not write it because we don't have anything to write here. The first is what are the effects of polarization? If the molecules gets polarized, you can see electric field gets reduced. Is it?
Yes.
We get an dielectric constant which we call as a relative permittivity also. We have seen that ER value, K value in earlier cases also.
Yes, yes.
Okay, let's discuss about some properties, key properties of dielectrics. So first one is dielectrics basically don't conduct electricity, as I already told. Okay, because they have kind of insulating nature, but they become polarized if you put them into the electric field because they are polar molecules. Their molecules are polar. Okay, they don't have free charges to move here and there, but their configuration of the molecule is such that they can become polar in presence of some electric field. Is that clear?
Okay.
About the dielectric strength, what is dielectric strength? That is basically the maximum electric field which a dielectric can withstand without breaking its configuration. Okay, without allowing the electricity to get passed. Understood?
Yes, sir.
Okay. The third is inducing the charges. Basically what happens, the charges induced by polarization are generally called as bound charges. Okay, which only present on the surface of dielectric. It is not the case that it will come up to your surface. No, it won't be able to jump up to your surface. It will just present on the boundaries. Is that clear?
Yes, sir.
After polarization they will just be able to come up to the boundaries. That's we done with the polarization. Okay, I will just discuss some application of the capacitors, and by this we are done with this whole chapter. Mm, one, I will suggest you to solve the NCRT for this, and one problem is there. Ladder capacitor, I think. Maybe if you see the ladder capacitor and all these things, these problems you can solve it from your NCRT. Okay.
Okay.
Energy in the capacitor we discussed already. Yeah, like okay, applications we already discussed because it doesn't have too much applications, right? The series and parallel are two things which is already a part of an application. We have already discussed that thing. So that's all for this capacitance topic.
Okay.
Okay. Anything else which we were yet to be discussed? I don't think from my side, I don't feel anything is yet to be discussed. Okay, one formula, one cylindrical capacitor and spherical capacitor is there, and I think I gave you as a homework part.
Yes, sir.
Have you done that?
No, sir.
Okay, no problem. So should I discuss it here?
Uh, which one do you think is tough? Because I haven't done it yet. I haven't gone through it, so I have no idea.
Tough is like if you look, if you are able to do any of them, like Both are similar kind of, the shape is different. Okay.
Okay.
So look, I'm going with the cylindrical capacitor. Okay.
Okay.
Or yeah, I'm going with the either cylindrical. I'm going because in the cylindrical we need logarithmic and all. Okay, we will be solving log and all, so I'll be using cylindrical capacitor kind of thing, and you can do it for the other one.
Very
What
good.
was the spherical one? Okay.
Yeah.
All right, so how we do for the cylindrical capacitor? Okay, where is that? Let's make a figure out of it. Touch it. Okay, I have not opened it. Just let me check it. Okay. I should go a little bit down. Okay, it's not possible. Okay. This is capacitor, and this is another way. This is one capacitor, and we can have a straight line out of it. Start. I don't have any option. Okay, let's say this is, and here also we can change the line. Okay, let's say this is your cylinder, right? Now I will take the same cylinder, just take a copy of it. Will take the width to be lesser than this and put it inside. Can you see I have two cylinders with a similar with the same what I can say. Let's increase the width of it. Maybe. Pratham, now can you see we have a cylinder,
Yes, sir.
two concentric cylinders we have. Okay.
Uh-huh.
So what will be the advantage of this concentric cells? Now you have two options. Like you can say either electric field is present outside or inside, whatever you want. So let's say positive charges are there outside. Okay, and here we have positive charges also, and assume the same number of positive negative charges are also inside. Let's make it from inside, not from outside. So what kind of electric field will be there? You can see we can have some straight electric field can be there. See this? I need straight things. Straight lines not making sense. Should be cancelled out. Get cancelled out. Now you can see I have some electric field all over the circuit, right? Is it clear? We have these kind of electric field basically. Okay. If you see what is the center of it, so I can say this is my center. Yeah, this is my center. Okay. Around this center we have an electric field. Can you see this? Now what is my task? My task is to calculate electric field. If I just make this from the top view, how it will look like? It will look like something like this. Okay, you are having two concentric cells. From top view, it will look like this, and electric fields are looking like this. From clear, from the top you will see like this, and from inside you will see like this, and we will be having this as a center. Is that clear? Pratham, let me know if it is clear. I'll move next.
Sorry, I was muted. Yes, so it is clear.
Okay, it's clear, right? Now just assume 1 to be the radius r1. Let's say from here I'm saying this is the radius. Yeah, wait, let me change that first. Let's say this is the radius r2, and this is another radius. So two different radius we have to take. This is r2 and this is r1, and okay, r2 and r1. Now I got this point, but how I should calculate the capacitance of it? Any idea? Pratham, any idea about the electric
No.
field? No, right? Look, I know one thing, that it's a very simple thing. I know one part, that capacitance should be equals to somewhere around change in charge and change in potential. Mean to say how much potential difference is there in between and how much charge difference is there. Is that clear? Like
Yes.
how much charge is there, how and how much potential difference is there. But how I can get this part? This is the task to be calculated.
Okay.
Okay. So what should I do here? Can I go with something called flux? Because for potential I need electric field at each point, right? Because
Yes.
potential, because I can get charge from somewhere, I know that thing. So I'm not concerned with the charge, the concern is about the potential. Potential, I can say dv equals to de times of dl. If I integrate this one, if you see
Yes.
here, okay, that is the thing. Now I needed this electric field. How I can get? I will say I will make another cylindrical Gaussian surface. My Gaussian surface will be cylindrical in nature, because if you see, if I make this as my Gaussian surface, right, is a cylindrical wave. From here it will be longer wave, some inside of some radius r. Let's say this is the random radius r. If I make a Gaussian surface of this value, what I'm going to get? I can say what is my flux. Flux is nothing but the total charge inside divided by epsilon naught, and this
Yes.
will come out also equals to E times of A. Is it?
Yeah.
So can I say the total charge is nothing but electric field multiplied by whatever the area I'm taking?
Yes.
Okay, and what is the charge? Charge is a constant thing. Electric field, let's take something. What is the area? If I see area, what is the surface area? This is the part, right, which is concluding in this surface area and the electric field. So can I say that is nothing but what happened?
Yes, sir.
What is this? Just what happened? How the boundary comes up from here? Uh, okay. I don't know where the boundary went. Okay, leave it. We'll see it.
What is happening?
No, I don't think like I wrote something, but everything has been gone. Okay, let's say this is one circle, this is another circle. Okay,
It, I think just press Control Z. It's
I tried
nothing.
that, but it's not working. Yeah, leave it. Okay, so what I did, I have taken this as my Gaussian surface, right? This was my Gaussian surface to be taken here. Now, we have calculated something electric field. What was that formula? Q equals to EA epsilon naught. This is what we calculated, right? So epsilon naught E times of A. What is the value of A here? Surface area, right? What is the
I
surface area? Pi
so
r
H
square
L.
multiplied by whatever the height is there. So I can say,
अच्छा,
yeah, pi r square h. No, no, wait. 2 pi r h. I
yeah,
just want to.
exactly.
Okay. Basically, 2 pi r square h will give you me the volume. Okay, just. Yeah, so this is what we have got. Charge equals to this. Now we will be using this formula to compute our electric potential. Okay.
Okay.
So what we can do here is we had to calculate charge, right? No, we had to calculate electric field. Okay. So what is electric field from here? You can say the charge divided by 2 pi r distance h into epsilon. What is potential? E multiplied by dA. Just take the same thing. If you see out of these, charge is constant, 2 constant, pi constant, h constant, e constant, right? What I'm varying, I'm just changing my radius because I'm calculating here, then calculating here, then calculating here, then so on. So dr, 1 by r dr. If you see, change in potential is nothing but q by 2 pi h times of epsilon naught log times of r. Is that clear?
Yes.
And what is r? It is going from r1 to r2, right? So this becomes r1 to r2. Okay, so finally what we have got the formula, that is total charge divided by potential. Write it, 2 pi h and the log of r2 minus log of r1. Is that clear?
Yes.
Cancel, cancel. What we have got in final? 2 pi height divided by logarithmic of r2 minus logarithm. Okay, this is log r1 and total multiplied by epsilon. Clear?
Yes, sir.
Okay, wait. This epsilon naught is supposed to be at the top, not here. So it will go upside. You can
Yes.
also rewrite the same thing like log a minus log of b can be written as log a by b, right?
Yes, sir.
So c comes out as 2 pi h epsilon naught divided by log of r2 minus r. This thing. Understood? This is the
Yes.
formula. Now look, if you have given cylindrical capacitor with a finite length, then you can directly use this. Is that clear?
Yeah.
But just assume instead of this height, because right now I have finite height 1 2 something, but if in case it is given as infinite, this side and this, then what you can do is simply, in that case we can't calculate the net capacitance. What we can calculate in that case is capacitance per unit length. Clear?
Yes.
And it also makes sense, right? If you can calculate capacitance with this configuration, okay, if you can get the whatever it is with this particular configuration, so you can calculate capacitance per unit length. Okay, that will be beneficial. And or also in that case you won't be getting charges, maybe you will be getting this density. Understood?
Yes.
And whatever, if you have seen the formula, it doesn't contain anything which can represent the charge. So solely it depends upon the geometry of your capacitor. Clear?
Yes, sir.
All right. So look, this is all for the today's class. Because look, one option is that I can start a new class. Another is, okay, which chapter to be covered next?
Sorry, sir.
Which chapter we are supposed to cover next?
I don't think The next chapter we have to cover.
All right. So it's a last class, right?
Yes, probably.
No, like from my side, this is the we are done with this chapter.
Concept is, yeah, okay.
Then I think if this is the case, so I can say it is the last class, is it?
Yes, sir.
Okay. So before this, I'll just give you one more problem. Okay, let's solve one problem. Mm, Okay. Mm, Can I give it as a homework part, or
Yeah, homework works.
I'm not sure how I can add these problems in this PPT. Okay, look, so for homework, I will send you another PPT. I won't send this part because I have not discussed anything special in this, right? Just when
Okay,
this formula is there and this derivation, I will suggest you to do two derivations, one by yourself. If you understood the concept, you can write the formula 2 pi epsilon naught h divided by log outer radius minus inner radius. Okay,
okay.
for similarly, you have to do a derivation for concentric cylinders, spheres. Okay, the one thing is you want to be getting the answer in log. For example, here you have got logarithmic answer. Now there you want to be getting answer in log. Just one is numerator, denominator, something you will be getting there. Okay,
Okay.
that will be there. Logarithmic will not be there because some more symmetry you will find here. Less symmetry is there a little bit, but
Yeah.
there you will have more symmetry. So that is the case. Understood? So from my side, I'm done with the chapter. Okay, if you see anything which may we have not discussed, so yeah, you can come up with one more class. That's it. You can do. Like from my side, I have ended the chapter. Okay.
Okay, sir.
Yeah. So if you want, I can solve one problem. Like I'm giving you one problem
Yeah.
which you can solve in the class itself. Okay.
Okay, sir.
Then it will be beneficial. Okay, let's do it. So maybe this block, a bigger one. I can use this. Okay. So solve this problem. Okay, out of this we have four sections. Maybe four or five. Yeah, four sections. So like this. Mm, Assume these to be straight. Okay, three and here one section. Okay. These sections we have clear. No, it
Okay.
becomes five sections. Right? These four sections we have K1, K2, K3, and K4. These K1, K2, K3 are the dielectric constant of these different sections. Understood?
Okay.
You have to get me one more thing. I can give you the values. That is, the total area is A, the distance is B. This area, this particular area is A by 3. This particular area comes up to A by 3. Okay, that two thing is there. This or that it's an obvious thing that this also becomes A by 3, and this thing is dy. You have to calculate the net capacitance of this configuration. Okay,
Okay.
so yeah, you can try this one. It's a good problem actually. Maybe I can say this is the point where you have to get the net capacitance. Okay, Look, whenever the figure is given to you and they have not mentioned which direction, so simply assume that in this horizontal direction, there will be some must a net capacitance will be coming out. Okay, so maybe this point terminal you can choose, this terminal you can choose. Around this, you have to get the net capacitance. Okay, so I'm clearing it little bit. All these areas are 1 by a by 3, and this is d by 2. That's it.
Okay. I got so K1, K2, and K3 will be in series, and then K4 will be in parallel.
Hmm. Okay,
So
so
by doing that, I have got an answer quite
okay, what is the net capacitance you have got?
okay. It is something like 2 E naught A
2 E naught.
upon
Okay, look, um, actually its answer is very big.
yeah.
Okay. Yeah, so what you have got?
I think okay. 2 2 E naught A upon bracket में 3 upon K1 plus K2 plus K3 plus 1 upon K4.
Actually, that goes incorrect a little bit.
Okay,
Understood? That goes little bit incorrect.
I'll recheck.
Okay, look, no, don't do that. Okay, I'll just explain this one. Then you have to solve this one also. Let's solve the problem itself. In this configuration, basically, I have given you two spheres. It has charge sigma 1, it has some density sigma 1, it has density sigma 2. Radius are given this. Okay. After the moment I close the switch, how much charge will be transferred, that you have to tell me. Okay.
Okay,
And for this, I'll give you a hint. Note this question, so it will be helpful for you to solve.
okay.
If you see carefully, the whole thing is K4, right? I know all these are something like parallel conditions. So I can say this is K1 wala, this is K2, and this is K3, is it?
Yes,
But look, not like this actually. You can do this like this also. But these plates are not like this. Okay, these plates are like this. Um, in this configuration, something around. Because basically it was a this kind of capacitor was given to you. Okay, what they did, first they put something in it, then like this and this. Okay. Then you have got something like, so they are asking what is the capacitance in between. Okay,
okay.
wait. I gave you the wrong question actually. You have to calculate it from here or here because in this you can't calculate it from this open terminals. You can't calculate. You can only calculate from here and here. It is my mistake. Okay, I will explain this one. Just you, the condition was like this is one capacitor, this is one, this is one. So you will be getting something like this, and this, right? But if you see, you have another thing that is like this. You have a single capacitor here that is this. Is it so? How you can connect it? Any idea?
Mm, maybe from the starting of the rod.
Okay, look, we what will happen? Can I say this is nothing but this because it is also K4, K4, K4. Can I say?
Yeah.
I just made three sections. So this whole thing will cut into this K4, K4, K4. Now you can solve this part. Okay, how you can solve this? These two terminals are connected, connected. These two terminals are connected, connected. These two terminals are connected, connected. Okay, something like this.
Sure.
And this final plate, if you see, that is connected to each of them. So make a connection in between. This side, this final is connected to each of them. Make a connection like this.
Okay.
You can get A, you can get B, and you can solve this. Understood? C1, C2, C3, C4, C4, C4. So basically, you have three conditions. If I say for a single one, if I just write C equivalent, what you are going to get for the single one, that is C4 divided by C4 plus C, right? So what answer we are going to get in final? C equivalent will be nothing but C1 C4 divided by C1 plus C4 plus C2 C4 divided by C2 plus C4 C3 divided C4 C3 by plus C4. Clear? And for C3 C1 to C all these you can directly calculate. What is that? C dash is nothing but C times of K. What is whatever the values. So E epsilon naught A by D times of K. What is that K? Whatever the dielectric is. So for different value, let's say I am writing it as R. So you can K. Is that clear? Although when you substitute this value, the answer will be little bit big. Okay, answer will not be a direct answer. Clear?
Okay. Understood.
Understood. You can just try this one after in a homework. Try this one. It's also a good problem.
Okay, sir.
Pratham, I have to take next class just now.
Yes, sir.
Okay, so I can end it here. I will see if I have one more question so I can give it to you. Wait a minute.
Sure, sir. So what was the hint for the second question?
Second question, the hint is I said the total charge transfer. Okay. Possibility is that you don't even have to charge transfer. The thing is, charge is only transferred. You can just take it as a bucket of water, another bucket of water. Okay, I said how much water is going to transfer. It depends what are the level of water it is. So here in this case, you have to check the potential. Understood?
Understood.
It's basically potential matching. If potential difference is there, then you will try to transfer charge such that potential becomes equal. If potential, like basically, charge will transfer until unless your potential becomes equal. That's it. So this is the condition.
All right, sir.
It is potential based.
Okay, sir.
All right. So this is all for the today's class. Like I don't have some questions. Basically, I have but have to fill. Okay, one problem is there. You can write it. Okay. Wait. Not here. Yeah. This is terminal A. This is terminal B. You have to calculate net capacitance.
Okay.
Here net capacitance. Here net capacitance. Okay.
Sure.
So two problems. And in NCRT, now one problem is there, which is this. Okay, I think this is not in this chapter. In the current electricity is there. Okay. So yeah, that's all for the today's class, Pratham. We
Okay.
can end the session by here, and I think this is the last session of ours, is it?
Yes, sir.
Okay. So tomorrow you won't be taking any session, is it?
I'm pretty sure there won't be any session.
Okay, so fine. Like from
Okay.
my side, like chapter is completed. Okay.
Yes, sir.
So yeah, that's all for the today's
Okay.
class.
Thank you, sir. Bye, sir.